Okay, welcome to topic 5, chemical equations and calculations. I'll just remind you, as I normally do, that this isn't intended to be a replacement for attending the lecture. Okay, this is more of a supplement if, for whatever reason, you want to come back and have a look at the lecture again for a bit of revision. Okay, so obviously in the lecture we're going to do some work on a lot of work actually on the whiteboard, which isn't going to be included in this presentation. Okay, so this might make a good revision or something like this. Let's begin with chemical equations. You can see here we've got an explosion. That's fun. So the conversion of one substance or set of substances into another. Okay, so any substance that we start with is the reactant, and a new substance that is formed during the reaction is called the product. So here's two really important words. We've got reactant and we've got product. Okay, so we start with a reactant or reactants, it could be more than one, and we produce a product or products, it could be more than one product as well. Okay, so it depends on the reaction. All right, and we put this together into a chemical equation. So here's an example. When hydrogen and oxygen gases are mixed, they react slowly to form water, but if they're ignited, they react very, very vigorously and even explosively, forming water vapor. So that's a really good example. Okay, when you've got when you've got just the right ratio of hydrogen and oxygen, and this is called the stoichiometric ratio, and we're going to actually have a look at stoichiometry very soon. So the stoichiometric ratio of hydrogen and oxygen, that's when you'll actually get a very violent and vigorous explosion. Okay. Now you can see here we've got an illustration where we've got what might be some hydrogen, H2, and some oxygen, O2, and they're reacting, and you can see we've got more hydrogen than we do oxygen, and if you've got just the right ratio, there's going to be 2 hydrogens for every oxygen. So in this way, the ratio is actually very important. Okay, the ratio of your reactants is very important for our reaction. Now, something that we need to learn about to explain this phenomenon is the law of conservation of matter. So this law, often called the mass law, states that in chemical reactions, matter is neither created nor destroyed. Okay, so just remember that law of conservation of matter, matter is neither created nor destroyed. We're not creating matter, we're not destroying matter in a chemical reaction. So we're never destroying matter, we're never creating matter. Okay, and sometimes this is called the law of conservation of mass. How do we know if a chemical reaction has taken place? Well, there might be a change in colour, there might be production of light, there could be the formation of a solid, so you might have a precipitate forming in solution, so smoke might form in a gaseous mixture, so in the air for example. There could be a coating on a metal, so you might have an oxidation coating, so you might have, if you imagine a piece of iron that's outside, okay, next to the beach somewhere where it's nice and salty and there's lots of oxygen present, and it rusts and we get this coating of oxidation, and this is a chemical reaction. There might be a formation of a gas, so there might be bubbles forming in solution, you might see fumes being formed, so visually being able to observe the formation of a gas as well. There might be the absorption or the release of heat. Now you might be holding a test tube and it might start to feel warm, or it might release so much heat that actually we're seeing a flame now appearing from our chemical reaction. Here's a quick exercise. Now let's have a quick look at this. This is actually a chemical reaction that's occurred here. We've got a battery that's been immersed in a solution, and we're producing some oxygen gas and some hydrogen gas. All right, so what is the clue here that a chemical reaction has occurred? Now this is an electrolysis reaction. So electrolysis of water produces hydrogen and oxygen gas. So what do we see? Is it a colour change? Do we see the formation of a solid? Are bubbles present? Or is there a flame that's being produced? Now I tell you what, if you were to ignite this gas that's being formed, most certainly I think we'd be seeing a flame being formed, wouldn't we? Because we've got oxygen and hydrogen present. But in this case, it's going to be bubbles are present. How easy is that? Very simple. We're going to start very simply and we're going to build up to some more complicated concepts as we go through. What is a clue here that a chemical reaction has occurred? So we've got a colourless hydrochloric acid which is added to a red solution of cobalt nitrate, turning the solution blue. Our hydrochloric acid is in our, well, this looks like a pipette, but it might be a burette, and it's being added to the cobalt 2 nitrate, and it's turning the solution blue. So it's what kind of a hint? Is it the colour changing, a solid forming, bubbles being present, or a flame produced? Of course it's the colour changing, okay? These aren't very difficult. And what is the clue that a chemical reaction has occurred? Here, a solid forms when a solution of sodium dichromate is added to a solution of lead nitrate. So this is a very interesting reaction where we're now forming a precipitate. When a solid forms in a solution, that's known as a precipitation, okay? Or a precipitate forming. The solid is referred to as being the precipitate. And obviously, a solid forms. All right, here's a chemical equation where we've got methane and oxygen being our reactants, and carbon dioxide and water are our products. Okay, so methane and oxygen, or methane and oxygen, are added together to give us carbon dioxide and water. You can see we've got 2 reactants and 2 products. So chemical reactions involve a rearrangement of the ways atoms are grouped together. Okay, so bonds might be broken and bonds might be formed. These are covalent bonds that are being broken and covalent bonds that are being formed in this case. So a chemical equation represents a chemical reaction. Reactants are shown on the left of the arrow and products are shown to the right of the arrow. Okay, very, very simple. So it shows that with the progression of time, methane and oxygen are converted into carbon dioxide and water. No matter has been created or destroyed. Okay, now hang on a minute. If we look on the left-hand side of the arrow, we can see that in total, just on the left-hand side of the arrow, we've got 4 hydrogen atoms. But on the right-hand side of the arrow, we have only 2. Now, this reaction has not been balanced. We're going to get to balancing later on. In this particular example, matter is actually being destroyed, and this is incorrect. This is something that we're going to cover later on, very soon actually. So we know that atoms aren't created or destroyed. We want the same number and type of atom on both sides of the arrow, which isn't occurring in this example. Okay, so here's an example of an unbalanced equation. So CH4 plus O2 gives us CO2 plus H2O. But it's not balanced because we know we don't have the right number of hydrogen on both sides of the arrow. Okay, let's balance the equation now. We might take 1 molecule of methane, CH4, plus 2 molecules of oxygen gas. That gives us, on the left-hand side of the arrow, gives us 1 carbon, 4 hydrogens, 4 oxygens. Okay. Now on the right-hand side of the arrow, if we add another water, we can have 1 carbon, 4 hydrogens and 4 oxygens. So it's balanced. So the balanced equation is going to be CH4 plus 2O2, then the arrow, that gives us CO2 plus 2H2O. So these numbers out the front are known as coefficients. And when you're balancing a chemical equation, all you're allowed to do is add coefficients. You're only allowed to add these large numbers out the front. You're not allowed to change any of the subscript. Okay? This is balancing a chemical equation. So a chemical equation is a symbolic representation of a chemical reaction. We know that in our flasks and our beakers and our test tubes, we don't actually have little CH4s floating around, okay? This is a symbolic representation so that we understand what's occurring in our chemical reactions. So to write one, we identify the reactants and write their chemical formula with plus signs in between them. So we can say, okay, in this example down the bottom, we've got aluminium plus iron 3 oxide, and so on. Okay, place an arrow after them. Now this stands for the process of converting one set of substances into another. So identify the products. In this case, we've got aluminium oxide plus iron, and if required, we need to place a plus sign in between these, which we've done. Now, the physical state, solid, liquid, aqueous, or gas, is shown for each substance as well, and that's what these little subscripts are in the brackets down here. So solid, liquid, aqueous, or gas. Okay. Now, if certain conditions are required, we'll write these above the reaction arrow as well. So if this needs to be heated, we'll just write heat above the arrow, for example. Okay. So solid is a solid, liquid is obviously a liquid, a gas is obviously a gas, but aqueous simply means it's been dissolved in water. So if you see a little AQ there, it means it's dissolved in water. It's in aqueous state. Step number 4, we balance the equation. So the number of atoms of each element is the same on both sides of the equation. So this is balancing like we did on the previous slide. We indicate the relative number of molecules or formula units of reactants and products as coefficients. Okay, so this is where we're using coefficients at the front to balance. Let's have a quick look at this one. Is this one balanced? So we've got aluminium, iron 3 oxide, aluminium oxide, and iron. So how many aluminiums do we have on the left-hand side of the arrow? We've only got 1, but we've got 2 on the right-hand side. So obviously, this hasn't been balanced. And also, the number of iron is not correct either. So what we can do is balance this simply by adding a 2 out the front of the aluminium and a 2 out the front of the iron. So now our equation is balanced. Okay, so we've got 2 aluminium solid plus iron 3 oxide solid gives us aluminium oxide solid plus 2 iron liquid. Okay, this is actually the Thermite reaction. Very interesting. If you enjoy getting onto YouTube, for example, Thermite, that's this reaction. It's very exothermic. It's quite impressive. So here's an example where we've got some